In this problem, we're given the graph of an absolute value function defined as the function f. We are to draw a transformed function g, which is simply defined to be 5 times f of x. And then we are to write the formula of the transformed function g at the bottom of the question in the answer box shown here. So to do this, it turns out drawing the new graph doesn't necessitate that I have its equation. For example, this notation says that the output of g, or the y value of any point on my transformed graph, can be found by taking the output of any point on my original function f and multiplying by 5. It also shows that we are not changing the value of the input when we go from a point on f to a point on g. I could summarize this in the following way. To get a point on the new function g, I can take a point on the function f, x comma y, and I can find where it gets transformed to by simply leaving the x coordinate of my point alone, but my new y value here, which is the output of g, think of that as my new output, can simply be found by taking my old output of f and multiplying it by 5. So my new output, or my new y value, will be 5 times my old output, or my old y value. So since my original output on f was labeled y, think of the output on g as being 5 times y. This makes an efficient process for you to take any point on the original graph and find where it gets transformed to, given that our transformation was defined this way. So let's pick a few points. It turns out with the drawing tool in the original question, one of the points has to be the low point of the absolute value function. So I will start there. On f, we have the point 0, 0, so I'll start with that one, but we'll pick a few more. Let's pick 3, 3, for example, on f, and why not pick negative 3, 3 as well? And I will transform all 3 points to the transformed point on g by following these directions. I am to leave the x coordinate alone. That's pretty simple. It was 0, I will leave it 0. For the new output, I simply take the old output, y, and multiply by 5. 0 times 5 is still 0. Repeating the process, leaving the x value alone, multiplying the y value by 5, 3 times 5 is 15. Repeat the process one more time, copy the x coordinate, do not change it, and multiply the output by 5, 3 times 5 is 15. When you get good at this, you may not even have to organize the information. You may be able to look at the graph and say, my new point will have the same x value, so let's look at this one. So the new x value will still be 3, so it's going to appear directly above or below the original point. Then since I'm multiplying the output by 5, its new height is going to be 5 times higher than the original height. The number 3 here, as a y value, says that the graph is 3 units above the x-axis. We're in the business of multiplying by 5, so it'll be 5 times that height, in this case 15. Since 15 is off my scale, I imagine it would be up here somewhere. Remember the point 0, 0 got transformed to 0, 0. In fact, any x-intercept on any function would stay the same with a vertical stretch because any x-intercept has a y value of 0, and 0 times any number is 0. In our case, we are multiplying by 5, but it doesn't matter what number is chosen for the vertical stretch. 0 times any number would be 0. And having a y coordinate of 0 means you're on the x-axis. So x-intercepts always stay the same with vertical stretches. So 0, 0 stays the same. Negative 3, 3, we kept the x coordinate alone, indicating that my new point will be directly above or directly below the original. Since we're multiplying the output by 5, 3 times 5 is 15, and I picked an unfortunate point because it would be outside my window. However, it gives me the opportunity to show you how fast you can find new points given this rule. For example, 2, 2, if I leave the x coordinate alone, multiply the y value by 5, 2 times 5 is 10. So again, my point will be directly above since I'm not changing the x value, but my y coordinate is now 10, which is 5 times the height above the x-axis than my original point was. This distance is 2, the new distance is 10. I'm not sure I should attempt to connect these dots because it would be a very crude drawing, but if you allow this to be called an acceptable line segment, but I will give it a try, doing the best I can to draw an actual line segment here. You may see why we call this a vertical stretch. If this was the original graph, we are actually changing its shape in a way that looks like I've pinned down the bottom of the graph, say, to a table, and I'm able to take the original graph and pull it upwards and stretch it upwards, which gives it the appearance of being skinnier. Now back to the original question, I will start with the point 0, 0, and notice indicated by the icon, you have to have the lowest point as one of the points you're drawing. So 0, 0 stayed 0, 0. Don't worry too much about where you put the second point. If you let go of your mouse, you can always change it. So remember that 2, 2 became 2, 10. So I will move this second point up here to 2, 10. But remember, this question also wants me to write the formula for g that would produce this graph. So to do that, remember that f of x, my original graph, had the formula f of x equals the absolute value of x. So my formula for my transform function g would have the formula g of x equals the 5 times f of x. But remember that f of x is equal to the absolute value of x. So I'm simply substituting the notation f of x with absolute value of x. So looking at the given statement and what I've written here, all I've done is a lot of copying, except for where I saw f of x, I replaced it with the absolute value of x. So going back to the original question, click on the answer box. At the bottom of the question, be sure to use function notation g of x is equal to 5 times the absolute value of x, and you can get that just by writing abs, parentheses x. You can click preview to see not only is the syntax okay, but the syntax that I chose to write does indeed give me the absolute value symbols here.